Right now, we're summarizing again those congestion patterns, and it turns out that all those congestion patterns can actually be reproduced with relatively simple traffic flow model, such as the intelligent driver model, but also others. And we can reproduce those surprisingly many different kinds of congestion patterns with the same model, even the same model parameters, apart from changing the inflow into the system, both the upstream flow and the inflow through the on-ramp. And then it's possible, in principle, to represent the possible outcomes in terms of what we call a phase diagram. And over here, you can see the upstream flow on the freeway. Here is the on-ramp traffic flow. And the sum of it gives the overall traffic volume downstream of the on-ramp. Okay, so if we go from the bottom left of this graph to the top right, where the traffic volume is increasing. And so from that point of view, it's no surprise that there will be a transition from free traffic to stop and go waves or homogeneous congested traffic, right? What is more surprising, however, is that we have different kinds of congestions, unstable and stable. And we have also different outcomes for small perturbations in the traffic flow and for large perturbations in the traffic flow. For large perturbations, you can have those additional traffic patterns, moving localized clusters and pin localized clusters, right? Like what we have just seen with the overtaking trucks in a sense. So those are predictions, and the fact that for the same flow conditions, we can have different outcomes depending on the history of the traffic flow is represented by the wording that we have a multi-stability in the traffic flow. Okay, there could be different outcomes, in other words. Now here's one of the papers you may want to look at and maybe even present to the class later on. The interesting point is that there is empirical data, and that empirical data actually fits the simulated data quite well. I should say that the simulation of the traffic patterns occurred before we had evaluated that empirical data, and so from that point of view, it nicely anticipated the findings in the empirical data. Large and small perturbations. You have small perturbations when there is a little variation in the density along the freeway. If there is a large density compactification at some places, like a platoon of vehicles where there's little distance between the following vehicles, and this is a large perturbation, right? Is that clear enough? Now, in the meantime, we can say there is an analytical theory of traffic flow. And this allows us actually to understand many of the phenomena that have been observed and their characteristic features that can be found in the empirical data. And what are the conditions under which what kind of phenomena can be observed. Plus, we can actually calculate the extension of congestion patterns and the associated travel delays, okay? I mean, travel times, in other words. This can all be done once we know when traffic starts to break down, which is, however, a stochastic process. So we can't anticipate exactly when one truck will overtake another truck, and these kinds of stochastic events will largely determine the moment where traffic flow breaks down. And that's why you want to avoid breakdowns in the first place and delay them as much as possible if you cannot avoid them. And now the question is, how can that be done? And once we have understood the reason why and how traffic flow breaks down, actually this can inspire new kinds of adaptive cruise control systems. We've developed one also with a big car company, and has been tested and worked pretty well. Now, of course, today cars are getting ever smarter. There's onboard data acquisition, something that we could call perhaps perception. There could be inter-vehicle communication. There could be cooperative traffic state determination, which we could call cognition. There could be adaptive choice of the driving strategy, which we could call decision making. And of course, also the driver could be informed, but first of all, traffic assistance would be given, not only to the individual vehicle, but we'd like to create a situation where the traffic flow altogether is stabilized and the capacity is increased. So over here, we are comparing the normal driving mode of vehicles with a modified driving mode where we change certain parameters by a certain factor. Okay, so you can see that over here. So here the parameter is reduced by a factor of 0.7, or here 0.5, and over there that parameter is being increased by a factor of 2. Now, depending on where you are as compared to the traffic jam, you would have different combinations of parameters. And it turns out that within the traffic jam, it makes a lot of sense to reduce that safety time gap slightly to increase the capacity. That, however, tends to reduce the stability of the flow, and in order to compensate for that, we'll need to increase the acceleration at the jam front when cars are going out of the jam front. So you can see, depending on the relative location, there will be different parameter combination that will be basically decided by the adaptive cruise control system itself. However, the system will need to be able to determine where in relation to the traffic jam the vehicle is actually located. Okay. Now, just wanted to maybe, while I'm showing you this simulation of stop and go traffic using the intelligent driver model, to show you that we can understand the kind of problems that we have on our streets, I'd like to mention now a lot of the cars in recent years, when machine learning and AI came up, have actually taken a different route from what we have done over here, which was basically trying to, that's the idea, to centrally control the movement of all the vehicles. And I will show you here that this is not necessary at all. Here we don't have a traffic center. First, we have stop and go traffic, which is caused by the on-ramp flow, which we have discussed before. But now we will equip a certain percentage of vehicles with an adaptive cruise control system that measures relative velocities and distances and accelerates slightly differently, as discussed before. And you can see it dissolves the traffic jam. Importantly, we don't need to control each car in detail by a traffic control center over here. Rather, we have changed the interactions between some of the cars. And as you can see over here, even if only, say, 40% of cars are equipped with that technology, this already has an overall effect on the entire traffic situation. So Increasing the percentage of equipped vehicles will dramatically reduce the traffic jam, but you don't have to equip all vehicles with that technology for this to work. It has also even more dramatic effects actually on the travel times. Now, how are we doing this? I think it's still, as compared to what most car companies are doing with self-driving cars, is still revolutionary because it's hard to believe even. So in principle, we are using, say, Internet of Things technology, that means sensor technology that measures the situation in the environment of the car. Not necessarily do we need a lot of sensors. And then based on real-time data, we introduce a real-time feedback, and thereby we're slightly changing the interaction between the vehicles, some of the vehicles at least. Now, traffic jams turn out to be the result of self-organization between vehicles, but it's an unfavorable self-organization phenomenon. However, we've seen that there are many different possible outcomes of self-organization, right? Such as different kinds of congestion patterns, but also we can understand free traffic flow as self-organized outcome of the interactions between vehicles. Just we need to have the right kinds of interaction. So basically what we're doing, we're changing the interaction slightly to change the overall outcome of self-organization in a favorable way. So with the Internet of Things, we can now make self-organization work 300 years after Adam Smith's invisible hand concept.